So yeah, okay, good. Okay, good. So first of all, I would like to thank the organizer for this opportunity of speaking today here. So I am Jorge Casanova, and I work at University of the Basque Country in Bilbao. And in this talk, I'm going to talk about diamond-based quantum technologies, about the activities of my group in this to construct correct. Essentially, my plan is that sensing or quantum, at least from natural applications of quantum technologies, right? In some quantum sensing profits or let's say the weakness of quantum computing, right? But you will see later, right? So probably because of all the hype regarding quantum information that we are experiencing, right? I don't know, yeah? Okay, okay. So you probably in what it is called the second quantum revolution, right? But before this second, we have the first quantum revolution. The first quantum creation of the quantum in conception we have nowadays about quantum mechanics, the way we have to deal with equations, we have to. And actually, when I was preparing this talk, I find this picture about the Solvay conference, and apparently, right, people said that this is the moment in which modern quantum theory, right, was created or was discovered, right? We can discuss about epistemic later, if you want, not now. And also the people was commenting the people here, right? Einstein, Dirac, Heisenberg, Marie Curie, if I'm not mistaken, von Neumann, and then this first quantum was essentially quite focused on the and some devices which are not so macroscopic, superconducting circuits, right? And it is important, right, because things that never had and I mean everything is pretty far away from the real world and these things. Okay, one of the things that I wanted to comment, essentially, this first quantum revolution, right, is not only about the creation of the theory. Actually, from this context, many technologies appear, and these are technologies that are totally immersed, if you want, in our industry and in our academics at many levels, right? These are theory, are technologies that emerge directly from this first quantum revolution. Here I have some examples of the this standard resonance use, of course, for academics, for research, but from the point of view of the industry is everywhere, right? Essentially in material science, yeah, it has already. And of course, yes, the laser, right, which is everywhere. Examples of technologies, right, which emerge essentially and were good, and with quantum computation, right, with quantum computing. This is the creation of the transistor. And actually, well, probably you all know about this Moore law, right? Okay. Essentially, I think it's this line, right? Have about the mechanics, the people was able to put step by step more and more transistors in dense integrated, which essentially power. So this is another example which is essentially everywhere here in my mobile phone, in the computers, everywhere. And it's a technology that directly emerged from the first quantum revolution. Okay? Good. So this is just right, such that you can really understand the transformative power of the knowledge, essentially, right? Well, I would say that right, and this is the moment in which we are now, right? Essentially, matter, right? In particular, quantum, right? Okay. Included this picture that essentially the for example, was really using the quantum superposition, right? They essentially were analyzing the signals that ensembles of particles of hundreds of thousands of millions of particles emit, right? So in thermal states. Let's think, but we're not explaining. However, established regarding, okay, so we were doing basic science here for several years, right? And then we have these 4 pillars, right? In communication, computations, pillars in which so I would say that it is work we are doing now is these 2 guys were they were able to control individual quantum and start to quantum superposition as well as entanglement. It's in physics and Sir Sarosh, who they were working on a slightly particular which is called they can was take it ground state and essentially sending, right? He was able to create, well, importantly, he was able to initialize, right, to avoid these thermal properties, to put all the population, if you want, for example, here in this at this level, right? And then he was able also to start to send in lasers and start to create quantum superpositions and in a kind of controlled manner, right? So Dave Wyland was using at the same time, Sir Sarosh in France was doing more mirrors, right? And essentially you had to the radiation there, and then afterward you can. So he was using math to control. It's quite interesting. Okay, but from a fundamental point of view, right, or at least in my opinion, so okay, these are quite pioneering experiments, and they were demonstrated that matter can be really controlled at its ultimate limit. Okay, from there, right? Okay, because well, here I have included a picture of some highlights regarding. This is Of course, this is a kind of subjective list, right? You can have your own if you want, right? For instance, in 1981 or 1982, things, right? Very soon he realized that the kind of computation, the kind of calculation he has to do very soon are very difficult, right? To solve analytically for sure, from the point of view of computing, impossible, right? So he had the idea, right, of essentially, okay, what control quantum systems or restricted quantum computing protocol, okay? And we dodge problem whose solution can be achieved much more efficiently using quantum resources than using classical resources, right? In particular, this was a kind of problem which essentially has no a direct application. Probably, yeah, it's just a kind of academic problem, but was, if I'm not mistaken, the first time a system with properties you can solve much efficiently a certain problem. And then we have other algorithms such as, well, which could be quite useful. For instance, the short algorithm that probably. Right. So from here, let's say here I was talking about only software problems, right? Yes. Problem, right? Has to be developed. And apparently, the first 2-qubit quantum computer was demonstrated in Oxford, right? For this to create something. And then, okay, yeah, so the people. This was a very nice experiment in 2005. The science group it probably this 14. So they were put in a kind of a string, right, and to control it pretty well, right? Their internal degrees of freedom and then, of course, probably you are. So big companies, right, enter into the game. In particular, Google. Different. The so-called quantum supremacy or quantum advantage. As you all know, again, in 2019, Google declared that they really reached right, because to they claim right, and of course, supercomputer. They continue fighting. Okay, so it's a kind of okay. Era, right? This noise intermediate scale quantum era, a quite substantial science now to see if can really with classical several fields and several, I guess, very promising one could be those related with optimization, quantum chemistry, these kind of things, right? Okay. So, okay. So we have have software as well, essentially people which are creating appropriate this software will which we have many companies here, right? Spanish ones actually. There are some of them there, as well at the same time. So we need big companies. Let's say in the development of the hardware, right? So this is more or less nowadays the game. Okay. So well, I think this because of efforts, right? From the academia, from the companies, funding, right? So yeah, that's good, right? So this is not working yet because because it's because of the complexity, right? So the first in this picture about this first quantum byte created in Innsbruck, right? So this picture looks more or less nice, but in the end, typically in matter we don't have qubits, except in nuclei. So essentially, you have to be able of encoding the information in several internal levels of a certain, and we have also because of the machinery, it's more or less we have the coherence, right? So the rest of the universe is forcing us to thermalize our system, right? So we want to create entanglement in a controlled manner, but we have to isolate these systems from the rest of the universe, but at the same time we need to leave there a window to manipulate, right? The matter in the way we want, right? So through this window, I mean, we are not the only ones accessing. The rest of the universe is entering there, right? So they are introducing some noises in our systems. Okay. So of course, these are the kind. I mean, we have here the Schrödinger equation, right? And let's say the excited and the ground state that we can select are solutions of this equation. And of course, because of the linearity of the equation, so this is also a solution, which is a quantum superposition. For instance, here we also can have entanglement. Well, one of the problems can you see here, right? You can see the problems here. So essentially, we have this decoherence, and these are the most famous decoherence channels that we are all experiencing in our system, right? The first one is really horrible in many setups. It's called the dephasing, and essentially it's a kind of really quantum noise, right? We could have some magnetic fluctuation that creates some random relative phases which are totally destroying the information we wrote, right? And we could also have bit flips, right? So also it's a kind of energetic type of, we could have even the ground state in our register. So for the moment, it is true that we could have some quantum memories, we can initialize them, right? And we can manipulate to create entanglement, superposition, but only up to a certain extent. So let's say nowadays the difficulty is to really scale our hardware. I took this picture in the lab of Christoph Wunder, and you can really see here we have this vacuum chamber, right, which is essentially there, and only in that reduced part, because of all the classical machinery we have outside, let's say the conditions, right, the appropriate conditions of isolation to really construct, to really allow the nature, if you want to emerge quantum properties, right? But you can see all the machinery we need to create these things, right? So the complexity is really an issue here. Okay, so then in this slide, so I really wanted to summarize a bit what I was telling you. So regarding our state of the art in quantum technology, so we have quantum registers that can be encoded in nanometric scales, right? Even Armstrong scales when we are talking about some atoms, right? So nowadays we also have the technology, the classical technology that allows us to initialize, control, as well as measure our systems, right? We can interact our registers in a controlled manner to create superpositions as well as entanglement. So as probably you all know, the entanglement in some way is the money we have to pay to achieve some kind of quantum advantage, right? So that's something that we have to create it. However, they are extremely sensitive, really sensitive to external perturbation. This is our problem, right, for quantum computing. What about sensing? If you read again the list. Okay. Actually, this is very good for sensors, right? We have systems, quantum systems, which are encoded in nanometric scales. We can initialize, and they are extremely sensitive, right, to external perturbation. Then, what about if we, instead of thinking on quantum registers, manipulate information, we have a sensor, right? Of course, the problem is that now we have to find applications and and the scenarios in which these kind of things could be useful in some way, right? So that's why I was telling you that maybe, okay, so in this manner you have the, with this list in mind, so probably you can understand that, so essentially this last represents, the weak part of the technologies devoted for quantum computing, but this is really the window for doing quantum sensing. There is a kind of natural manner of understanding this, right? Okay, so in this field of quantum sensing, I think it is fair to say that nowadays we are working on this, but it is fair to say that essentially it has really a strong relation with the standard nuclear magnetic resonance, right? It's really related, right? I would like very large and has produced right. So nuclear magnetic resonance is an area, right, by itself that has revolutionized fundamental science and application, right, because it allows us to understand central interactions that appears in nature between radiation. It allows to study these systems, and also it has produced several applications, such as, for instance, the reconstruction of complex molecules, right, or even proteins, right? And also, as it is represented in this picture, also it has led to several applications regarding medicine. This is the case of magnetic resonance imaging, right? To obtain essentially, well, and that's why it's a kind of very common diagnosis method, which is used nowadays everywhere in hospitals, right, worldwide. So it's a kind of application. Actually, and despite all these applications, right, NMR techniques have strong limitations regarding sensitivity, okay? The reason is that essentially this NMR signal depends on the nuclear spin polarization of the sample we are. Actually, for instance, typically we are reading the radio frequency signals emitted by the protons in, for example, on the water of some of our tissues, right? But actually, this signal in the end depends on the spin polarization. If you want, roughly speaking, the number of spins pointing up minus the number of spins pointing down, right? In a thermal state, this number is really little. So as I will tell you now, and especially at room temperature, right? Because at room temperature is the scenario when we want to really develop these things because of sensing, because of logical conditions, because of the applications on materials, or even on medicine. Okay. Okay. So in this animation, probably, right? So imagine that. Well, also, this is a kind of simplification of how standard NMR works, right? So imagine here we have some piece of matter, right? It has atoms have nuclei. So the problem is at room temperature, right? Well, I am saying millimeter size sample, the kind of samples using standard NMR, okay? And what these pictures try to reflect is that, roughly speaking, we have the same number, which means that we have the same number of spins pointing up than pointing down in all directions. So that means that essentially the radio frequency signal is zero, because essentially direction, I mean, that's a kind of complicated issue, but trust me, for the moment, it's like this, right? So what happens, what the people do nowadays to avoid this type of situations is essentially to introduce a very, very strong static magnet. Okay? The animation really worked, but my idea was that during this animation, some of the spins have to rotate it, right, in the direction of the magnetic field. Okay? So by introducing field, in some experiments, even this magnetic field is of the order of several Teslas, right? What we have is a slightly, so that means that our sample got a right vector, if you want. Okay. So now what we do is to introduce some static, some radio frequency field to take this magnetization, and because of this static magnetic field, this magnetization starts to rotate, and then externally what we are doing is to read the signal with standard detecting coils, this of the sample. Well, so here I was telling you that we were working with millimeter size samples, but what about if we go to micrometer, right? If we want to right, for these applications, so what happens, of course, is this one, because of the vector is even smaller, and then essentially we cannot get anything, right? Because the signal to noise ratio is essentially is not favorable for us. Essentially we are reading noise, right? Okay, just to be more, first panel I included let's say a summary of the previous animation. Let me check. Okay, I still have some 10 minutes before the break, if you want. And to be more quantitative, as I told you, so this NMR signal depends on this quantity, which is related with the magnetization, and this quantity is the probability of having one spin up minus one spin down. This can be computed with, for example, using the Boltzmann distribution, right? And you will see that even at significantly large static magnetic fields of 2 Tesla and at room temperature, right? Essentially, this quantity is about 10 to the minus 5 for hydrogens, which is one of the most reactive, let's say, from the point of view of the electromagnetism isotopes. Okay. So that means this 10 to the minus 5 means that only, again, roughly speaking, right? Only one nuclei among 100,000 is really contributing to the signal we are reading. That's very bad for a standard NMR, but it's very good for you, right? Because that means that we have a lot of room to improve using other technologies, right? And actually, because of this very bad number, that's why typically millimeter size samples are required. This is a typical tube that the people use in standard NMR experiments, okay? Okay, and that's the moment of introducing quantum sensors, right? Because essentially we want to avoid these problems, okay? So this is the moment in which micro and nanoscale NMR enters, and actually this represents a radical, right? Is to replace this standard NMR apparatus by a quantum sensor, right? As it is shown in this picture, right? There are several quantum sensors, different platforms, but in particular this is especially successful because essentially it works very well, right? I will summarize later, a little bit later, the properties of these nitrogen vacancy sensors, right? But here, I think can be understood in this picture. So essentially, and because of the tiny dimensions, because this is essentially a diamond unit cell, where this is approximately 3.5 angstroms. This can be located very, very close. So in this scenario, or in these conditions, even the individual molecule, in this case a type of sugar, right, would change the states of the sensor. What to do is to read to track in some way the internal state of the sensor, and then if we see that analyze emitted by the sensor, we want to infer properties of this, let's say, of this, for example. Okay. Actually, this is the field of micro and nanoscale, maybe NMR, right? And actually, it's promising several applications, such as the individual spin detection and control, right? Actually, this part has already been achieved in different labs at room temperature, right? And even at lower temperatures of 4 Kelvin, which is not crazy, right? It's much more controllable than the millikelvin required for circuit QED, probably, right? So a substantial amount of people is already starting to work in that field, right? Also, it produce high resolution magnetic resonance, because one of the problems is that, okay, for magnetic resonance imaging is the same one, right? So we want to analyze the magnetic signals emitted by, I don't know, the protons of my water, of my tissues, right? And this has a very small polarization, but as this is a kind of quantum technology, we can initialize it very close to 100%. So what about if by doing quantum to transfer this polarization to the nearby nuclei? That maybe enhance the polarization of a tissue, and then is much more sensitive to for the protocols of magnetic resonance imaging. Okay, and also for the field of nanoscale, right? So maybe to study what happens with individual molecules and try to reconstruct its 3D aspect. Okay, so we have here, I wanted to show you what is an epicenter. Okay, so here we have a diamond unit cell, so you can imagine that essentially this is repeated many times in a chip of, I don't know, millimeters or micrometers, right? So here, these black balls essentially are carbon-12 typically, right? Which is an spinless particle, quite boring, right? It has we cannot do anything. However, nowadays it's possible to create this type of defects, right? For instance, what the people do is grow this right? And from time to time, some nitrogen enters into the lab. And if at the same time, so we have here nothing, meaning so this little defect here, which is essentially nanometer cube, essentially gets we have several electrons which are a little bit confined there. Were participating in these bonds, which nowadays are. So I mean, one can calculate this structure. Okay, and these are the properties from the point of view of the quantum application. So of course, this system, right? That I mean, there are nowadays more or less accurate theoretical models in which one can describe these properties using systems of 6 electrons, right? Which are in some way located in this little region. Okay, it has several levels, right? It has some electronic ground state and excited state, which is a transition, which is quite optical. Actually, yesterday we were in the labs of University Carlos III, and we had the opportunity to really see how bright these systems are, right? We have the opportunity of watching with our eyes this transition. Okay, this transition is used for measuring and for initialization. Has a high splitting. It has the so as you can see here we have some let's say hyperfine ground state, and also here we have two degenerate hyperfine states, right? Then if we introduce some static magnetic field, which is typically in high precision experiments, the people try to align with this axis, right, with the MB axis. So essentially we remove this degeneracy, and essentially we have three levels which are pretty well separated, right? And then one of them could be the zero. I mean, we have a qubit, right, operating at room temperature with pretty competitive coherent times, right? Let's say at room temperature, people nowadays can get T1 times of milliseconds and T2 times by using some decoupling techniques trying to approach this 1 millisecond, okay, at room temperature. At low temperatures of 4 Kelvin, the things are much better from the point of view. Okay? Okie dokie. All right. And before the break, I would like to comment one of these here, right? Because it's this one, right? So essentially, as I told you, here we can create, I mean, we polarize down, right? Meaning we are on the zero. This is this one, right? Because if I apply a green laser, right? I shine a green laser to the system. What happens is this, right? Thus, this MB starts to emit photons, right? Actually, in the red. Okay. Also, if I am plotting, if I prepare an initial state, let's say pointing up on the excited state, again, if I shine a laser, what happens is this. Okay. I don't know you really saw the difference, but my intention was to show that the rate is lower, right? So they emit photons in a, I mean, at a slower rate. Okay, and that's the one. On the zero state is brighter. Okay, emits more photons, and that's something that we can detect externally even at room temperature. Okay. Well, this is again this. Actually, now I wanted to focus on this transition, so that's why I reloaded this slide. And actually, this transition, of course, can be a little bit. This transition can be written in a more, let's say, quantitative manner. Actually, okay, as I told you, this electronic ground state has this splitting, right? And okay, let's say the reason by which the zero is brighter than the plus one or the minus one can be seen here, right? So if we shine actually up, right, get excited, right, right. It does not change the spin, okay? However, if the system is polarized on the plus one and minus one, and we send a green laser, so this state can also fall down using this radiative transition that emits a red photon, but also this state can also take this other non-radiative transition in which essentially the population gets in some way blocked in a certain metastable state that the people, I mean, this metastable state is non-radiative, and take this with care, because it is radiative but in a different manner. So that's why we cannot really differentiate it. And actually, it gets trapped for a quite large amount of time. And in the end, I mean, the problem here, the issue is that essentially because of the existence of this non-radiative channel, so essentially the 0 and the 1 has a different luminescence, if you want, right? So if we are on the 0, I mean, this channel is always on and it's always emitting photons. However, if we are here, right, so this channel is not really radiative, right? So from these numbers, you can really see, you can really try to imagine which are the amount of photons we are getting, right? Typically, the measurement processes involve sending a laser for approximately a microsecond. People at the end, 1, 2, 3. The last two are typically used for initialization, but let's say 1 microsecond for measuring, right? So if you divide 1 microsecond by 12 nanoseconds, you can see that, well, the amount of photons one is receiving. But again, because of the problems related with standard quantum technology and actually with the sensitivity of our detectors, in the end, what we are getting is this, right? Essentially, the number of photons we received, the average number of photons we received, if we these are histograms taken from this, actually from this paper, so this number could be improved a little bit better, but not too much, right? So we have the MB, let's say, polarized at 0. So typically we receive 0.016 photons per measurement, right? So that means that we have to repeat and repeat and repeat a lot, right? Actually, the difference between 0 and 1 is not so high. And this is because essentially, let's say photons are emitted in all directions, so we are not recoiling each photon we got, and each time one photon hits the detector doesn't make click, right? So the efficiency of the detector are pretty low, right? However, and only using the fact that this is slightly much better, right? Okay, emits more photon, and actually this is the definition of the luminescence. So if you make this calculation, you will see that this is 0.3. That's why the people say that the zero state is 30% brighter than the one. Okay, let me go on. One can, let's say, reproduce, for example, radio oscillations, which are represented here. Okay, so before entering, I guess, in this part, I think already 40 minutes, so we can make a break, because the next part is more about applications, right? So, okay, we can 5 minutes, 10 minutes break, or they simply by sending the laser, and I think I later have a slide about that, right? So you can really shine a laser and you see bright spot, right? You say, okay, we have an epicenter there. That's more or less the way. So you have set like this, sending a laser like this, yeah. So I continue. All right, so, okay, no problem. Fine. Okay, so, slide, actually, you can see that actually, let's say, the histograms, what I am trying to plot is that the probability of measuring 0 photons are quite similar when they are on the 0 and on the 1, right? And slightly larger when you are on 0 than on 1, right? By just profiting, just by using this little, right, one can really make quantum mechanics, right? Actually, the type of signal one is expected to reach is this one, right? Imagine that, okay, we are in this, we have this this scenario, we put some static magnetic fields that we create, we have a pretty clear splitting, and then we polarize here, and then we send some micro radiation to produce transitions, right? And that's something that can be done at room temperature, and in the end, this means that we are getting this quantum state, right? Then that means that the signal, from the point of view of the photons, we want to obtain written more or less like this, right? Essentially, is the probability of being here times the average number of photons one would get if you are in 0, multiplied by the number of shots, right? And the same story with the other one, right? So that means that from here, from this expression, and just by measuring this S of t, right? Essentially, I can obtain this probability and reconstruct the quantum state, right? That's a quite general way of recalling the info. And in these simulations, so essentially what I wanted to show you is that it is possible to really reconstruct the typical kind of things we all do when do quantum mechanics, right? The only point is that we have to repeat and repeat and repeat a lot this experiment, right? So in this purple curve represents a radio oscillation, right? Actually with some decay that I introduced it because of t and t2 times. And for example, these blue circles here represents the signal one would obtain by just watching the photons. And as you can see, here I have into 10,000 shots, right? It really matches more or less fine, right? Regarding the luminescence, we can really reconstruct the quantum state, right? Sorry for being repetitive, but this is room temperature stuff, right? Okay, well, I was doing I was commenting there are other materials as well, which also behaves in a similar manner. For instance, this is the silicon carbide, one of the polytopes of the silicon carbide, right? And actually, it presents differences, meaning advantages, potential advantages with respect to the diamond. One of them is that, okay, as this is silicon carbide, we have different isotopes in the lattice, carbon-13 and silicon, right? And silicon. And this is good because we have several registers, meaning qubits, right, on the lattice, much more than the carbon, right? Also, it presents some uniaxial defects. Well, forget about this. It's not because I didn't introduce this. And also, it has a large temperature dependence, which is, again, very bad from the point of view of the processing information because it's really sensitive to the temperature. But from the point of view of a sensor, that means that we can construct a really local thermometer for thermometry experiments, right? And of course, this could have also potential medicine applications, right? Because essentially one of the applications that the people is doing nowadays regarding tumor is that essentially what you want to do is to hit some local parts of the body such that the tumors get, in a way, more hungry, right? And then if you introduce some chemotherapy stuff, right? So yeah, so they got infected much more than other tissues, right? So that's why we would like to see with a very local precision let's say the temperature of the tissues. Okay. The difference with carbide is that can be the luminescence was 30%. In this case, it's even worse, 1%. Right. So that means okay, that we have to repeat and repeat more. Okay. All right. So regarding the distinct people is nowadays working in applications regarding nuclear magnetic resonance with MBs. So I think can differentiate between these two regimes. One of them is the case of single MB, right? The idea is to now, and nowadays it's possible to implant these MBs very, very close to the surface. Okay, that means, and I mean, it's possible to demonstrate. I'm not going to do it now, but trust me, okay? It's like this, okay? So in these conditions, in this scenario, so the MB is sensitive to a little sphere, right? With a radius which is essentially more or less close to the distance between the MB and the surface, right? So that means that the MB is only sensitive to a very local region of the space in which even a single molecule could enter there, right? So that means that the MB is sensitive to a single molecule and maybe we can use it for and that's very important because nowadays it is accepted or it is known that the 3D aspect of molecules have really, essentially determines the behavior they have in the metabolism of different, let's say for example, in our body. Okay, the problems regarding this scenario, I mean, the big advantage is that we have a very, very local sensor able to understand what happens in really small regions of the space. And the problem is that the sensitivity, right? I mean, you will see, essentially, the sensitivity goes like 1 over the square root of, right? Where n is the number of measurements, so we have to repeat a lot, okay? Also, it has low spectral resolution, meaning that I'm going to obtain some peaks, and the width of the peaks depends essentially on the T1 time of the sensor, which at room temperature couldn't be much larger than hundreds of microseconds very quickly, okay? Is already there, right? It's already producing results that can be applicable, right? And the idea here is that, okay, if we want to increase the sensitivity of our sensor, I mean, one natural way of doing that is to put more MBs, right? In a scenario like this one. Of course, we are losing this nanometer scale, but again, it's possible to demonstrate that in this scenario where you are shining a laser and in some way you activate a relatively large amount of sensors, right? Essentially, it can be demonstrated that now the sensors are reactive to micron size volumes, right? This is a volume which is totally far away from the abilities of standard nuclear magnetic resonance, right? So we can have access to NMR or really small regions, not as small as the nanometer, but already quite competitive, right? And also it has different applications, right? Because it has a very large spectral resolution, because nowadays there are methods, actually we have developed some of them, in which one can get, let's say, we can enter in what is called the Hertz regime, so we can get peaks with a resolution of Hertz, which is already, I mean, comparable with the resolution one can get in standard NMR, and also the issue of the sensitivity, right? In this scenario, each MB the MBs are individual, right? So essentially we have to repeat less because now the sensitivity goes like 1 square root of m times m, where n is the number of repetition and m is the number of MBs, right? Of course, well, these two expressions are called the standard, perhaps a more futuristic application, right? Nowadays the people is also working on that, is that, okay, given that we have several MBs, what about if we create some entangled states among them, right? And entangled states are quite fragile, right? And some little perturbation will produce a much more strong reaction of the system, right? The idea is to, instead of working with this sensitivity, maybe we can reach this Heisenberg limit, right? If we are able to create entanglement among different states. And maybe, perhaps, many body system that we can entangle, what about we take it very close to a phase transition? And in that moment, the system gets very reactive, right? With respect to external perturbation. So having this behavior of this Heisenberg limit means that for the same number of measurements and for the same number of MBs, our experiment will be much faster, right? Very fast. Maybe fast enough to watch a chemical reaction, yeah, in real time. That's another futuristic application, okay? Okay, so, well, in this slide, I wanted to put some, let's say, some highlights of the field, right? Actually, this first one is very related with the question of cause, right? Okay. Essentially, on history, right? But and this is the first time in which single MBs were observed. So essentially, what the people are doing is what I am doing now with my pointer. So this is the diamond. I am sending a laser, and then if I find a spot, right, that means that this is a MB, start to emit photons. Okay. You can see the splitting to the three-level structure. Okay. And of course, the people very soon realized that beyond potential applications on quantum computing, because on that moment the people start to say, okay, we have now quantum computers at room temperature, right? Then the problems related with this start to appear. And very soon the people realize that we have very good magnetometers, right? And some, let's say, pioneering experiments appear mainly on the group of George Bragtrup in the University of Stuttgart, as well with Fedor Jelesko, right? And at the same time, also in the United States, in the group of Lukin and Ron Balsworth, right? I think it's very fair to say that early work regarding characterization measurement was also done by George Bragtrup and Fedor Jelesko, right, regarding the characterization of here. But let's say more or less these two type of experiments regarding magnetometry were more or less at the same time. Okay. Okay, and then these are more recent experiments, right? Trying to take this system and really exploit their properties. So, for instance, this is an experiment of in the group of Bragtrup. Maybe this is more interesting because essentially they were able to implant an MB at a nice distance from the surface and really start to see the magnetic signal emitted by some complicated polypeptide there, right? And actually this is very interesting because in an experiment done at 3 Tesla, which is a pretty large static magnetic field, which implies that the signal emitted by this guy is very strong, and they were able to really see, right? So this, let's say, this column is a lot about nanoscale NMR, and more in the direction of microscale NMR. We have these quite nice experiments in which they were using, as I was telling you, right, some MB ensembles, right, and they were able to actually make NMR of very small regions of the space, on very small regions, which are not accessible at all by standard NMR techniques, right? Actually, these regions are pretty interesting because maybe we can also think to, okay, potential applications are, okay, what do you want to, for example, the analytes emitted by a single cell, or what about if we want to analyze complex extractors that appears, let's say, at these scales, for instance, the membrane of a cell. That's very important, right? Because it's a kind of surface that separates the inner and the outside of the cell. And the people working on chemistry, I mean, they say that, let's say, all the relevant chemistry typically happens on the surface of the things, right? So we have here a tool to really understand this type of processes. And there were also several, let's say, applications and improvements regarding this field. So these are really this already on the applied science, or on the applied side of science. Okay. Okay. So perhaps this is a little bit more technical, but essentially, I think I can explain in a quite intuitive manner, because a lot of quantum control is involved in the manipulation of these sensors, right? So essentially, what we have to do, what we have in the end is that some sensor or some set of sensors, some ensemble, and actually it has some gigahertz splitting, right? And actually want to make interact this guy with, for example, with a certain nuclear spin which is in the environment, and typically this the energy splitting is on the order of some megahertz, depending on the static magnetic field we introduce, right? So from this point of view, these guys cannot talk among them, exchange interaction, because a pretty large energy gap between them, right? So what we have to do in an intuitive manner is to supply that energy difference from outside, right? Of course, introducing radiation. That would put this energy that we need to make these two guys interact, right? Of course, all what I am saying has to be supported from, let's say, from Hamiltonian theory and doing the things properly, but this is more or less the intuitive way, right? And actually, the standard manner of introducing the radiation is through continuous or pulse radiation patterns. A lot of things to here, right? Maybe, for instance, okay, this is the Hamiltonian that describes this situation. As you can see, we have here this energy gap. And for instance, if we introduce this microwave radiation in a continuous, meaning a continuous wave, right? So essentially, it is possible to take this Hamiltonian and transform in this manner, okay? And then, in this scenario now, this now is this one, right? And this omega is the amplitude of the electromagnetic radiation we are introducing, right? And just by playing with this amplitude, we can make them resonate, okay? That's more, okay? And the other way is to introduce pulses, right? And with pulses, these are, I mean, panel represents pi pulses of that exchange by the ground and the ground by the excited, right? And here, what we're looking for is essentially to create a pattern such that the period of our term is this energy difference. So that we are to rotate our and okay, as the case of a single nuclear spin is not really interesting enough, right? So essentially, what we are trying to solve are where essentially you have DMB, for example, here, and you have a quite dense forest of magnetic particles, right? And if you produce control sequences good enough, so essentially you could of this type of patterns here. You can see this type of where you can really, okay, this is one of the things we did several years ago, actually. But nowadays the people produce, okay, this is a quite updated result. What the people tend to produce are crazy, let's say, pulse sequences like this one, which is called droid, right? Because in this type of sequence, what the people is looking for is that, okay, what about this is devoted to the case of having several MBs, meaning an MB ensemble, right? And of course, if I want more sensitivity, what I can do is to put more and more to create more MBs in my chip, right? But these are quantum entities, and there is a moment that depending on the density, the chips, these MBs are starting to see among them, right? They could start to interfere because they are also electron spins, right? So now the people is trying to look for, say, sequences in which essentially what you can do is to remove the interactions between spins, between MBs, and at the same time make these spins reactive to external signals, right? In that manner, what you can do is to, let's say, increase the sensitivity of your sensors, right? Just by quantum control techniques as complicated as this one, okay? So as I told you, the way in which one delivers the radiation is very important. For instance, here, this is called the XY8 sequence, which is a way of sending pulses, in which one delivers pulses in different along different axes. So one rotates the excited to the ground along the along the x-axis or along the y-axis, right? And the people uses this sequence because it's pretty robust against controls or errors on the control, right? Okay, so actually, if one let's say if one let's send a program, for example, this sequence in a simplified scenario, one has an MB and, for example, one carbon. Actually, after this sequence, what one would expect is this one, right? So quite a strong resonance peak here, right? In the natural Larmor resonance point of the carbon, okay? But this is the ideal case, right? For instance, the ideal means that the pulses are delivered more or less instantaneously, right? However, in reality, pulses has a certain width, right? Takes some time to do it, right? And if depending on the length of these pulses, one would obtain is this more quite complicated dense of let's say forest of peaks. Okay. Well, the true resonance is still there, but as you can see, there appear other resonances at different points, right? And in particular, this is especially dangerous, right? Because this spurious resonance appears very, very close to the natural resonance point of the hydrogen, right? It's a totally spurious resonance, shouldn't be there, right? But it's there because our sequences are not ideal, okay? So one could end in a scenario to say, okay, I have detected hydrogen, which is on the surface of my diamond. Could be something like an spurious effect, right? Okay, for that, one can start to play with the quantum control techniques to avoid this kind of errors and this kind of mistakes or several others, right? For instance, in this experiment, what we do is to concatenate, for instance, several XY8 sequences, and then as there are many, many degrees of freedom that we can exploit, for instance, one of them is the relative phase among pulses among different blocks. Okay, yeah, that's something not totally easy to understand, but what it is easy is to see here the results, right? What we did is to have some diamond, and then we put some oil that contains a lot of hydrogen, right? And also our diamond has some carbon 13s, right? So this orange line corresponds to the experiment, right? That respect to the signal one we observe after applying a normal XY8 sequence. And as you can see here, you have this spurious resonance which essentially obscures, right? Essentially overlaps a little bit the presence of the hydrogen. But just playing with the phase among blocks of our sequences, so we got this blue, let's say, curve, which where essentially the effect of the carbon 13 is really reduced, right? So then we can certify that we were getting we were observing really hydrogen on the surface of the diamond. Okay. Okay. Well, of course, these quantum control techniques can be, let's say, exported to several other platforms, right? Because in the end, what we are doing a lot in, okay, we have could be an vacancy center for sensing or a certain setup for computing, radiation, right? And we observe what it emerges, right? And we have to trust that in between something good happens, right? So in the end, a lot of the things we are doing, right, is are related to quantum control techniques, and many of the techniques that we are developing for sensing can be directly exported for processing information. In particular, well, this was an experiment, or no, this is not an experiment. I will show you later something related to experimental results, but this is the theory in which essentially we apply the same type of sequences, let's say, in a system involving ytterbium trapped atoms, right? As you can see, that simply playing with the phases among pulses, you can get 2 qubit gates, which has very good fidelities in a much larger range than in the case where you are not applying directly these random phases, right? So the fidelity is much larger. If this is the fidelity compared with different errors, right? Let's say the tuning errors as well as errors on the amplitude of radiation. Okay. So that means that essentially the same type of techniques can be applied for other purposes. Okay. So well, I wanted to comment this experiment, right? This theory, because another, let's say, another route that the experimentalists are following is the, okay, for instance, this experiment that I showed you regarding ambient samples, which is quite pioneer, was done at a pretty small static magnetic field, right? And this is because, let's say, when you increase the magnetic field, the nuclear spins start to rotate very, very fast, right? And to track the signal is complicated, right? Because you have to put a lot of power in the rotations of the MB, right? So this is a kind of problem. However, to go from, let's say, hundreds of millitesla to several teslas is pretty good for the point of view of the spectroscopy. First, because the thermal polarization of the sample is much, much larger. So that means that the signal the sample emits is larger, right? And also, because of the several quantities that encodes structural information about the chemical compounds here gets enlarged, right? Okay, so then the problem here in this experiment was to say, okay, yeah, but we cannot track the information, this fast signal that the sample is emitting if we simply go from here to there. So that's why, okay, maybe in this animation you can see how this technique that was recently published applies, and nowadays we are implementing this in experiments, right? So essentially, our technique is a lot, again, about quantum control. In this case, we are encoding, we are using two channels, one microwave channel, which is essentially controls the MV, and a frequency channel to drive the spins on the sample, right? So essentially, at very large state magnetic fields, what we have is some magnetization vectors. Here we have 3 magnetization vectors corresponding to the 3 different quantities we want to measure, right? So with a first radio frequency control, right, what we are doing is to take this and to rotate to the and now the next step is to do essentially nothing, right, to wait a little bit, right? So we are in a scenario in which the static magnetic field is pretty large, and because of the deltas, right, so this guy starts to dephase, right? So the longer we wait, the more dephasing are getting, the more separating are getting, and now we have to apply some radio frequency field over the sample, right, and at the same time a microwave field. What happens is this one, right? So what I wanted to show here is that now we can control the speed of precession of our sample, right? So that means that we have a radio frequency field that even a larger magnetic field is in some way slow. So that's something that that can be easily tracked with our techniques, right? Of course, one can repeat this process several times, and of course, each time, and depending on the relative position between the magnetization vectors, the emitted magnetic field is different, and just by watching these differences, we can really reconstruct the information on this sample, right? Okay, this is the last one, I promise. Okay, maybe this is more interesting, right? Because this is the type of things, the type of signal we expect to get in our MV. After doing this type of things, this type of protocols, and then if we make the fast Fourier transform, in the end we are getting these peaks, right? Regarding, in this case, this was about, I think this is ethanol, right? And then we are getting the structural information and the spectral information with a precision that, as you can see, is on the order of hertz, right? Which is already competitive with the standard NMR scenarios. Okay. Okay, and of course, again, as I told you, this is a lot about quantum control, right? Of course, one can always try to complicate the sequences, looking for, let's say, improvements from the point of view of the sensitivity, from the point of view of the resilience against control, right? And instead of, let's say, sending simply continuous radiation, one can do it by blocks, and in the end, well, yeah, essentially this plot is more interesting. We are essentially watching which is more resilient against errors on the radio frequency fields, right? But okay, let's say the main message is that by complicating the sequences, we can get better results, right? With the same precision, more resilient against typical errors. Okay, and regarding some interesting application of these sequences, for example, actually this is a grouping with which we are collaborating. So actually, these quantum control techniques for this method can be used. Actually, they cite our work here, and they see this could be a kind of solution for application as interesting as, for example, let's say tumor detection of these things, because you can start to analyze with a very large precision the analytes emitted by cells which are suspicious, right? And because of the precision of the measurement, we can get that, okay, some chemical substances shouldn't be there, which are indicative of a disease in a quite early stage, right? So that's why this is a kind of important. All right. So another application is called this dynamical nuclear polarization, right? In which essentially, as I told you, so the in standard NMR experiments, so the nuclear polarization is really, really low, right? And people is looking for different manners of extending, of enlarging this polarization of the sample. But the good thing is that these MV centers, these systems, can be easily polarized with a laser pretty close to 100%, right, at room temperature, right? So if we do it in an ensemble, right, with several MBs, so the next step is via quantum swap gates, right, transfer this polarization to the nearby spins, right? And in that manner, we will end with a sample which has a very strong net nuclear magnetic moment, and this emits a very large, let's say, NMR signal that we can analyze with standard NMR techniques, right? Okay, let me see. Okay, yeah. One application is the tracking of metabolic routes of several drugs, treatments, right? For instance, okay, it could be a nice application. So imagine this is the diamond, right? And we can put here some fluid which is passing through the surface of the diamond. And then, for instance, here we have this chip with several MBs, right? And then if we are able to take the polarization, first polarize all the MBs and transfer this polarization to the atoms of the fluid that is flowing in the surface of the diamond, this substance will abandon the chip with a larger amount of polarization, right? That means that they will emit a quite radio frequency signal. So what about if now this is, for example, a kind of treatment for, I don't know, chemotherapy, right? So that means that after injection on the human body, we can follow pretty well, right? And we can see in which part of the body this substance is acting, right? So that would help a lot to the design of better treatments, right? Of course, there are several patents in this direction. In particular, well, this is a kind of hyperpolarizer, right? Designed in the United States, and actually is looking for this type of applications, right? So here we are experiencing several problems. One of them is the presence of some dangling bonds on the surface, which are a kind of electron spins, which could, in some way, let's say, avoid the transfer of polarization from the, let's say, from the MBs to outside. But nowadays we are working on, well, we already have a preprint in that direction that Hilario will present later, right? So, fine. You can ask him, right? Okay, and at the same time, this is also one of our recent works in which essentially we can also exploit the properties of dangling bonds, right? Here you can see much better which is the scenario. So imagine you have some nitrogen vacancy center, and here we have some electron spin which is on the surface, which typically is considered as a source of noise, right? We were considering this scenario in which we have some complex protein, right, complex molecules, and nowadays it's possible to attach several molecules, right, which are in some way free radicals, right? Now, the good thing about these things is that these free radicals interact quite strongly, depending on the distance, right? And that's the quantity we want to measure, because imagine this protein suffers something like a structural transition, right? Changes its aspect, right? That would mean that the separation between the labels is going to change, also its coupling, and if we are able to detect this coupling, we are able to say, okay, some phase transition happens in our molecule, right? Typically, this is obscured by the presence of some dangling bond, but what about if we think on the dangling bond instead of a noise source as a kind of antenna, right? Because it's pretty close, it's essentially in the surface, right? So it will interact pretty strongly with the things outside the diamond. So by designing, let's say, complicated sequences like this one, which is a castle-shaped manner, in the end, one can end in that one can encode directly through the dangling bond this coupling, the coupling between labels, right? Actually, one can demonstrate that essentially this complicated structure ends in a more or less simple, right, solution in which the coupling constant between labels appears here naturally, G, right? It is interesting that also the noise in this, because as you can see, this complicated structure has some, let's say, free evolution times in which the noise can be accumulated, right? But ordering the pulses in this manner, you can, the noise will appear in terms which are not touching the quantity we want to measure, right? So that's why this way of doing the things looks quite appropriate, right? And actually here we simulated the scenario in which, well, the blue line corresponds to the scenario in which we have some dangling bond, and the red one, the scenario when we don't have, right? And you can see that the contrast of the signal is much better, which means that the precision of the measurement will be also larger, okay? Good, you can see the preprint here, which is the guys, actually these two guys there, right? You can ask them more details, right? Okay, also, and if I have time, still 5 minutes or? Okay, good. Also here I wanted to comment that, okay, well, so essentially we have this device. We have to apply, this is a lot about hardware, right? And we have to carefully design this microwave radiation pattern, which are the quantum control techniques, but this is just one part of the story, because at the end of the process, one has to take one has to measure, right? And sometimes the information that the sensor emits is quite complicated, right, to analyze. So there is a lot of data processing at the end. In particular, this is quite interesting, the use of neural networks, because they are quite flexible to really understanding classical data, right? So these are neural networks for analyzing the classical data emitted by quantum systems, right? And actually, this is part of the work of Borja, who is there, right? Well, previously we did some pre-experiments in a different system, because it is easy to characterize, right? Actually, we use again this type of let's say complicated. This is an ytterbium atom which has some energy transitions, right? As you can see, when some electromagnetic wave enters into the system, okay, the Hamiltonian that determines the dynamics of the system is not very friendly, right? It's complicated, so that means that in the end the signal, right, that ytterbium atom will emit could be also quite complicated with a, let's say, because it is ruled by these dynamics, right? Of course, it depends on the regime, right? There are some regimes in which essentially the signal that the sensor emits is quite harmonic, right? Here the blue is our theoretical predictions, while the points are the, let's say, the experimental results obtained actually. I mean, you can check in this paper. It's an experiment that we did with a group of one can go in China. However, if you change a little bit the regime, so the signal is this red one predicted by our neural networks, while you can see that the experimental results are pretty close, right? So here the problem is that, okay, from this quite complicated signal, it is difficult to extract the parameters, right? However, neural networks can be trained with tons of signal like this one, right? So then we were checking what happens with the fidelities, and in the end we got on average that in this complicated regime, so the fidelities of the precision of the measurement is pretty high. It still can be improved with further, let's say, more sophisticated. Okay. Okay. Maybe this is one of my last slides. So I wanted to comment that, okay, this field of MBs essentially is producing several applications, quite crazy one, right? So in which the people really wants to construct something like a diamond helmet to really understand the radio frequency signals emitted by the brain, and maybe to analyze the brain activities, right? And this is, for the moment, this was quite academic, but outside of Spain, it's not as academic because there are several companies, but fortunately, right, in Spain we have Archimea, which is already entering, and several into the game, right? Actually, we have there Ivan, which is in the developments at Archimea, and as well we have, right, actually in the university in Leganés, in Tercero, which is already doing efforts on this line, right? Okay, and before thanking you for your attention, I wanted to tell you that if you are interested in your research, you can always send me, let's say, and also, okay, open positions, this line will be soon in my. Thanks for your attention. Yeah. Essentially, you start from some basic sequences which can be understood pretty well. I mean, the dynamics and something, and you start to put more and more layers of complexity, right? Because the first one is to say, okay, I apply some pulse sequences which are essentially rotate my spin at a certain speed, but then I want to, let's say, fight against different sources of error, such as, okay, what about if my pi pulses is not exactly like this, but rotates a little bit more like this, and then you start to put more and more layers of complexity. So it's a kind of accumulated knowledge, right? So in which the people started to construct, right? There are already several set of sequences which works pretty well, right? Both at the theory and the experimental level, and then you start to put more layers of complexity depending on your objective, right? Well, actually, depending, okay, for low densities of MBs, essentially we have individual sensors. They don't interact among them, right? So as long as you start to increase and increase the concentration, you have a model which is dipole-dipole coupling among all the elements of your net, right? It's dipole-dipole interactions everywhere. So, having said that, depending on the, I mean, you also have quantum controls to create icing models, these kind of things, right? And then this opens the door to really, let's say, look for specific phase transitions which are well documented on the literature, right?